welcome back to the channel. So this question is actually very similar to the previous day problem about lexical order of the numbers. So if you haven't watched that one and would like to know how to solve it, then I recommend watching that before. So for this one, it is a bit different because of the the runtime that we limited not to use the exhaustive way. So this is the solution from yesterday. So let's see if we can just copy paste here, and then this gives you a whole result of the array, right? So in this case, if you want to return a particular index, this is one index instead of zero indexing. So we can just return k minus one. And if we run this, you can see this is actually passing the test, but let's try to submit this. And I think it will give you a memory limit exceeded, because see how judging it is. Yeah, so this will run out of the memory. So maybe you say like, oh, I can just improve this by running to like k time and then just return current, something like that. Like let's say we just minus equals 1 in the beginning, because this one indexing, and then remove this result, and then probably just return current. Actually not sure if this works, but let's see. Okay, we don't need to append this. Just try to run it. And yeah, it works, but once again, when we run this, it probably gives you a TLE. All right, waiting. All right, this gives you a TLE. So actually try this different approach before. Oops. All right, so let's dive into like the way that I'm thinking about this. It's using a prefix tree or something, and then it's highly reference to this editorial. But I just want to like make a video so I can know how to do it by myself and how to explain it to other people. So let's look at a PowerPoint, and yeah, it's September 22nd question. I was kind of late. All right, so what this is doing is actually when we have this like 1, 2, 3, the tree, right? We kind of can find that the prefix in between them and see where exactly they will fall into. So instead of just going through it iteratively, we can see like where there are. So let's say I have like 210 that I want to find, right? So let's say given n equals 210, and then let's say k equals to 131, right? So here we'll have like 10 and then 11 all the way to 19, and then here you have like 20 all the way to 29, and then 20 will go on to have like 200, 100 will go in, 10 will go in, and 100 or something like that, right? And then eventually you go on to 210. So when you do this, you can do like a prefix thing where when you check 1 and 2, you know that the difference between 1 and 2, which is this level, is 1. And then the difference between 10 and 20, we just need to look at 20, is 10. And then when we go in 100 and 200, we said, oh, this is actually the difference between here and here is 100, right? So when we sum up all this thing, 1, 10, and 100, we get a result of 111. So what does it tell you when your result is 111 but your k is 131? That means the k, the 131st element, is not going to be inside of 1, right? Because all this thing contains will probably just include like 111 elements. So this tells us that, hey, actually the result you want might not fall under the leading which of 1. So then you can just go ahead and go to 2, and then do 2 and 3, and then you compare between 2 and 3. And then maybe it will tell you where it is, right? Because when you when you have 2 and 3, and then it's tell you, oh, this is 10, and then this one, and then 2 and 30 is 10, and you just add up and see where it's going to. All right, so this is like one case that you can do is, yeah, just check one case where let's say this is greater than, the step is less than the 131. the steps is less than k, then you want to move on to the other case. But what if it is inside, right? If it's inside, then let's say I want to find 111. And then I know that all these things sum up to be 111, then means my answer probably like be 199, right? So when it is less than or equals to n, that means that the thing you want to find is inside your branch. So I know it's kind of messy, so let's see. So if you know two cases, let's write down. So if you know it's in yourself, then you want to go from the current, you want to go into current times 10, right? Because you want to go into it and then compare it with your current plus 1. If it's not in you, not in, then you know it's the next one. So instead of going down, you plus 1 to yourself and go to your neighbor. Then your neighbor will compare to 3. So these two will compare each other, and then they will keep going with calculating and finding it. And then one other case is what happened if you hit, let's say, well, right? Let's say you given n equals to 137, and then your k is 100 or something, right? So when you have 1 and 2, you keep going, right? 10, 20, 100, and then 200, and then 1,000, let's say. So when you compare this the difference is 1, right? This is 1, this is 10. When you're trying to hit here 100, and then that's valid, but 1,000 is not valid, so you don't actually go in there. But 200 is actually greater than 137, right? So instead of using 137, instead of using 200, you want to use 137. So instead of using this, you want to use 137. And now the difference between 100 and 137 is not 37. It's actually 37 plus 1. Why is it the case? Because when we have 200 and 100, we're actually calculating like the 11 elements is from 100 to 199. So 100 is the first element, and then 99 is the last element, resulting in 199 minus 100 plus 1. Right? But now 137 is actually inclusive. So 200 is actually not inclusive, but 137 is inclusive. So in this case, you need to plus 1 after you do the minus, the subtraction. You need to plus 1 back here. So that's the one thing you have to be conscious about. All right, so just dive into code. I hope I actually explain things that slightly make sense. All right, let's say we start with current equals to 1, and then I will like to get I equals to 1 instead of using cases minus equals 1 or that, like keep subtracting k. Instead that way, I would like to increase I to hit k. So you can say while I less than k, then you want to keep doing this, right? So I will use the helper method to find like the steps that we're saying. So I can say steps equals to count steps, and then you want to pass in the current value. So what this count step do is actually it will just go on and count the steps, means like how many value in current and its neighbor. So what exactly it is actually this part, right? The 1 and 2. So we just calculate how many elements are actually in this triangle or in this tree. So then I said there are two cases, right? If it's in yourself, then you just want to step into it. If it's not in yourself, then you want to move on to the next one, right? So if I plus steps is less than equals k, means that it's two less of that, then you want to move to your neighbor. Then otherwise and you also need to add the steps into it. because we've done like 111 steps, but it's still not in there. So we just want to add all the steps to I, and then just move on to the neighbor. Otherwise, we just want to step into it and then start doing it. So we need to multiply by 10 to step into our child. And then we just increase I by 1 step, because from 1 going to 10 is actually just 1 step. Okay, it sounds about right to me. And then we just need to return current at the end. And now we need to write this helper method. Right, so this helper method is count steps, and then we pass in current. All right, so this helper method is try to compare how many steps are there in between me and my neighbors. So we can first set step equals 0, and then we do our neighbor equals to ourself plus 1. So let's say current equals 1, then neighbor will be 2, and then just going down, right? So when it goes down, we said, well, current is less than or equals to n. Then, at the end, you want to step down again. So your current is 2 times 10, and then your neighbor also need to times 10. Then right here, we can say steps. We're trying to find the steps. So we can say steps equals to neighbor minus current. But one thing to note is the thing we said, what about yourself is actually too much greater than n, right? So instead of doing that, just neighbor, you can do minimum of neighbor and n plus 1. Why is n plus 1? We actually mentioned that, like, let's say you're 136, then you want to do 136 minus 100 plus 1, which is 37, right? And then the neighbor is just like, let's say my neighbor is going down, right? My neighbor is actually going down. So now it's 200, but 200 is not the greatest one. That's why I take the minimum between my neighbor and n. So we see which one is the minimum, right? Kind of stuck. Okay. Then after we do all this thing, we just need to, for this helper method, we just need to return steps. So the steps can be passed down back to here. So this is the solution where current equals current equals 1, I equals 1, and then you just start doing it and just stepping in, and then this helper method. Right, let's try to run this. All right, and then we submit this. Oh, so one mistake I make is actually the steps is actually need to plus equals to, because you want to increment the steps every time. So like when you have 1 and then you have 10, you have 100, that's gonna be 111 instead of just reset it to be 100. So that's one thing that I mess up here. So let's submit it again and see what's the result. All right, then it passes this time, and yeah, so the runtime for this is actually of log n squared, I believe, because of the tree that you need to build. It's log n, and the space complexity here is actually of 1, which is constant space, which this memory is kind of cool right here. Let's see. Right, they say, oh, log n times log k. Yep. Right, so I hope this video is helpful, and I'll see you in the next video.